good. Okay, recording's on. Excellent. So we are starting a little bit late because we were answering homework questions. I also wanted to make sure that everyone was aware of the schedule for what's happening for the rest of the semester. So we're in week 11 right now. You have the things you should be working on right now are homework 3, which is due on Monday, and that is an online homework CAN data type of assignment. Then we have a formative assessment that I'll put up next week once I decide what it's going to be about. And then we swing into presentation modes. So I have the form for peer review in each of these. It's the same form on all of these things. And note I made the due dates Wednesday and not Monday. That way, if you have somebody is presenting on a Thursday, you don't have to turn it around until Wednesday, so almost a full week. It wasn't fair to do it on Mondays otherwise. So we have those happening. Where did it go? The presentation rubric is right here as well. And then, yeah, you'll have one more CAN data homework of some kind to do that will be due at the end of finals week, and then that's it. So we're winding down in terms of what's being asked of you. The things that I'm hoping to still get to before presentations start, today we're going to do the multivariate version of the time-varying predictors, and then talk about time-varying predictors that show individual differences in change, which is really the point at which any kind of person mean centering observed variable version of a predictor is not going to work, and you need a multivariate model with multiple growth curves happening simultaneously. So I have some specific examples of that I want to show, and then I'm hoping to do at least a little bit on intensive longitudinal data, demonstrate a location scale model, as well as 3-level models. So occasions nested in days, for instance, nested in people for intensive data. So that's what I'm hoping to still get to. I deliberately have not put the stuff up because I'm waiting to see how much time we're going to have. That way I don't over prep like I always do. If there are things you need help with your presentation analyses, please let me know. I'm happy to direct you towards resources, examples, M+ user guide examples or articles or things that would have your particular model. Most of you are attempting to do something that is new to you. So building off of what we're doing in class, which is exactly the point, but you shouldn't be expected to figure it all out by yourselves. So please let me help you if you need it. All right, any questions about schedule or ongoing work? No, we're good? All right. Zoomers, we're all good there too? One person's good. Okay, good enough. All right, then let's see here. I want to be in slide 40. That's where I want to be today. So I'm in lecture 4, slide 40. There's some more thumbs. Thank you, Zoomers. And make sure that the recording is still going. Yes, that looks like it's good. Always paranoid about that. Okay, there we go. So what we've been talking about, time-varying predictors. And the short version of this is that for the same reasons that we need a multi-level model for longitudinal outcomes, we need to worry about partitioning sources of variation into between versus within persons for predictors. It's the exact same situation. And the process that we've done up to this point is turn our time-varying predictor into 2 different variables. A level 1 version and a level 2 mean of the level 1 predictor goes in. So I prefer the version that we would call person mean centering or variable centering, in which the level 1 predictor is created by subtracting the person mean. That way it only has within person variance, and its slope in the model can only be the within person effect. Separately, orthogonally at level 2 then, the person mean of the level 1 predictor goes in, centered at a constant so that 0 means something. And because it only has between person variance and there's no between person variance in the level 1 predictor, the slope of the person mean can only be between slope. So easy peasy. Now, looking at the way of dividing the variances in this way makes it obvious that there's an asymmetry here. Why is it that we're representing between person mean differences in x with an observed variable, but we're doing it with a latent variable for the random intercept on the y side? And likewise, why is it that we're representing within person fluctuation in x as an observed variable, but on the y side it's a latent variable? So why don't we just make it parallel? Ta-da! Multivariate. Here, I'll do it back. That's the difference. So this is known as latent centering. It's known as multi-level structural equation modeling if you want to sound fancy. But the key idea is that you don't make a distinction in terms of how you treat X and Y. So X and Y are two different outcomes from the perspective of the model estimation. And you can look at relationships at each level via covariances or via slopes. Slopes allow you to do things like moderation and other kinds of, and indirect effects and other kinds of stuff too, which I wanted to show you how to do in the example. So this is the basis of it. It's in a nutshell. It's not that much more complicated. Where this approach tends to not work as well is when there's not a strong signal for the random intercept. So if you have a predictor with a really, really small intra-class correlation, there's not that much between person mean differences to be found. You can always compute a person mean in a data set. That will always work. But you can't always estimate a random intercept variance. So that's where it starts to fall apart. And also if you have not a lot of data with which to do it. So small sample sizes make this more challenging as well. So here is, I'll show you the example, but just to make the contrast as to how some other folks have talked about time-varying predictors and what not to do. So I showed you these pictures, I think, a couple weeks ago, but they bear mentioning again. This picture is inside the M+ User's Guide still. It is example 6.10. And in this picture, what they've done is use a growth model for Y. So the 4 Y boxes here, this is Y data, have an intercept and a slope factor predicting them. They have 2 time invariant predictors of x1 and x2 that are predicting the intercept and the slope. And then they have a time varying predictor A, where they have slopes going from A to Y at each occasion. If the time varying predictor does not have a covariance with the intercept and the slope, then this is a smushed effect that you get back here. And it can be a different slope across time, like they have it estimated as 4 separate slopes, but all 4 of them are still smushed, because it's not the effect of having more A than other people. It's not the effect of having more A than usual. It's some amalgam of the two. So we don't want that. The same problem is in the picture that I stole from the Levon tutorial on growth curves. This is how they talk about doing time-varying predictors. We don't want to do that either. So I want to show you, these pictures are what it would look like in terms of wide data. The example that I have is using multi-level SEM with long data. So I'm going to have a mixture of both types because people are working on both types at this point. So this is what we would, what should we do instead? So there's an article on your reading list. It's actually a book chapter, I think, from 2012. And they figured out in that source that if you allow a covariance between the time-varying predictor with the intercept and the slope of the other outcome, then these become within effects, not smushed effects, which is better, but then there's no way to put the between effect in the model. And you might look at this and think, okay, well, can I just like make a box for the person mean of Z and stick that in here too? And no, you can't. Essentially, the program might converge, it might not converge, but it will certainly yell at you because it would be redundant with what you already have. Like the person mean is redundant with these values that make the person mean, so it will yell at you. So what we can do instead is make a parallel structure. So let's say that Z doesn't change over time, but it does have between person differences. Okay, well, I'm just going to make an intercept for Z in the same way that I made an intercept for Y. And it's an empirical question whether Z needs a slope as well. So for those of you who are going to be working in this multivariate world, the first step of your process is univariately figure out what's going on for every time varying variable in your model. See if it has individual differences in change in particular, because if so, we need to have a slope structure on here. If not, maybe you can get by with just an intercept. Then the question is, are the relationships that you get out of this between or contextual? And this picture is showing the idea of what is known more generally as a structured residual. In structured residuals, which I have an example coming next week for that, what you're doing is essentially taking what was residual variance for Z, you are transferring it to a new latent variable. So in the code, it looks really silly because what you do is say, okay, I have a new variable that's perfectly measured by this observed variable. I'm transferring the variance from my observed residual to this new variable. The rationale to do it that way, though, is that you're essentially separating out only the within person information, giving it a new name. Then the level 2 model has between slopes instead of contextual. Without it, if the path goes from the original variable that has all the level 2 part in it still, it's the analog to constant centering, and the level 2 relationships are contextual. So this intermediate layer of variables is the new thing in the picture, structured residuals. And I will show you how to do all of that as well. So this is some pros and cons. We've talked a lot about this with respect to univariate versus multivariate. The big thing is that if your time varying predictor shows individual differences in change, then there's not a choice. It has to be multivariate because there's no way to make a box that will work for that. So, all right. Questions so far? We talk about what not to do, what to do. Zoomers, any questions? Roomers? I only have 3 roomers today. Yes?
So part of my project has been figuring out which intercepts, which random effects should be related in terms of just a covariance or like a regression path.
Mm-hmm.
Can you talk just more generally? I guess if you go to the other picture, it would make more sense.
Yeah, like this one, for instance.
So what is the difference when we have just a covariance between z-int and y-slope as compared to a regression path saying y-slope on z-int?
Okay. So by the way, I relabeled these. They were like squiggle something in here, and so these are my words trying to make that a little bit easier to follow. So the rationale for putting a slope is in your mind, like you're thinking of this like causally, like this is the predictor and this is the outcome. Somebody else could make a rationale for turning the slope around, like, no, this is the predictor and this is the outcome. At the between person level, all you have is cross-sectional information. It is arbitrary as to which way the slope goes. So I could take this relationship and turn it around, or I could take it and turn it into a covariance, and the model's going to fit the same because you're allowing a direct relationship between the variables of some kind. In terms of which to make fixed effects and which to make covariances, it would be weird from a linear model's perspective if I had a slope that goes from z-int to the y slope here, like this, without the corresponding path to the intercept. Because what that would be doing is essentially putting a z by time interaction in the model. Like that is conceptually what's happening right here with this path. It's a z by time interaction. And if I didn't have the path right here, then it would be like I left out the main effect of z, but I had the interaction in. So that from that perspective, it's weird. It's not wrong. I mean, you can just have these things all covariate and not worry about it, but it is odd if you have paths to what are functionally creating interactions without the corresponding main effects. Does that help? Maybe?
Yeah, but the idea is that you have to, whether it's a with statement or an on statement, is primarily conceptual. Like
yeah.
Why one causes the other.
Mm-hmm.
But in terms of the estimation, some of my models, I can get them to converge when it's just covariances, and I can't get them to converge when I, use these more like theoretically grounded paths. And I guess I'm like, I know conceptually what the difference is, but like in terms of the actual estimation, why I'm running into issues, when I use different approaches.
So the issue was estimation challenges when you put in fixed slopes as opposed to covariances? Is that the issue? Okay, between the random effects. Well, keep in mind that if you put in a fixed slope, then what you get back for the random effect variance is variance left over. So if your fixed slope is really powerful, you may actually end up predicting most of the random slope variance, and if it's a tiny amount that's left, the model could have trouble coming up with that number. So that could actually be a good thing from that perspective. Did I have a question? I thought I saw a hand up from the Zoomers. No? Okay, I'm hallucinating apparently. All right. Yeah. So let's talk about mediation, shall we? Because longitudinal mediation is a thing and it's often done wrong. The short answer is that mediation is only logically possible at the same level. So mediation is the idea of X causes my mediator, and the mediator in turn causes Y, and that's why X and Y looked like they were related, is because the relationship happens through this third variable. That's the idea of mediation. It's not a synonym for moderation. But in models with longitudinal variables, you have to look at what levels each variable has variance, and level 1 mediation is only possible if all 3 variables are measured at that level. But I made out this chart so that you could see the consequences of what is possible in terms of level 2 mediation, because it always is. So if I have all 3 variables measured only at level 2, that's the obvious choice. But what about this one? If I have a level 2x and a level 2m, so these are time invariant, but y is time varying, how is it that I can still have level 2 mediation? Any guesses? Yep, because there is level 2 variance most likely buried in this level 1 variable. So the level 2 mediation happens for the random intercept of y, or the random slope of y, if it has one, the level 2 part of the level 1 variable. And the same is true for all of these other combinations. It's the level 2 part of the level 1 variable. So I had a hard time explaining this once to a PI that I was working with on a grant. He had this row right here. It was a level 2x, a level 1 mediator, and a level 1 outcome. And x was whether or not you had an experience of sexual violence. It was measured in young women. And I think, and M was something like, alcohol use, and Y was like risky behavior or something. And he had this hypothesis about people who have had, bad stuff happen to them are more susceptible to making, choices about their alcohol, and drinking a lot can cause you to do things you wouldn't normally do. And it was a whole thing. But you can't have a mediation model within persons. Like, you can't talk about the reason that you drink more than usual and that in turn leads to more risky behavior is because you were abused as a child. Like, you were abused as a child the whole time. Like, that can't be the reason I drank more yesterday than today. So from a mediation standpoint, the chain is broken. In this example, you could have level 2 mediation. People with a history of abuse may be more prone to alcoholic behavior, and people who drink a lot may make bad choices, sort of like as a person level. But that can't control like time fluctuating kinds of things. At the level 1 model, you can still look at, if you drink more than usual, do you have bad outcomes more than usual? You can still look at that relationship, but it's not mediation. M+ or any other software will be very, very happy to compute an indirect effect of any kind. But whether that makes sense is a whole different question. Like, you could have the path going from 2 down to 1 to back up again, and you could look at the multiplication of those paths, but it doesn't make sense. So it's the level 2 part of these time-varying predictors that would have level 2 mediation. All 3 would have to be measured at level 1 and have variance at level 1 for level 1 mediation to happen simultaneously. But that's the example that I wanted to show you, is how to do something like that. All right. Want to see an example? Sure you do. You came, right? All right, I'm pulling up 4B, which I am optimistic that we can get through a good chunk of, if not all. So this is multi-level mediation, or longitudinal mediation, in variables that do not show systematic change. So this is a fluctuation story. These data are from chapter 8 of my book. They are real data that were doctored a bit to show some things. These data were collected in a sample of 5 days in 105 older adults, and they were looking at daily stressors, daily negative mood, and daily physical symptoms. And the idea is that something stressful happens, that puts you in a worse mood, and if you feel worse, mentally you might feel worse physically. So part of the relationship between stress and its translation into physical symptoms might occur with mood as a mediator. That's the story here. So in my pictures, let me zoom in here, there is an asymmetry with respect to boxes and circles for demonstration purposes, but also estimation purposes. The way that stress was measured daily was whether or not a stressful event happened. It is a binary predictor. So I opted in this set of examples to treat it as an observed variable and put in the person mean of stressors centered at 0.4. So basically the reference is somebody who had a stressor happen on 2 out of the 5 days, 40%, and treat that as an observed variable. That was, like I said, partially motivated just to show you the difference in how the code would look, but also because binary outcomes require a different type of estimation, either Bayesian or numeric integration. So it makes things a lot more challenging. Negative mood, though, this is an example of when I would have to do a multivariate model, because negative mood is serving as an outcome of stressors at both levels of analysis, but it also is a predictor with respect to physical symptoms. So when a variable has to be both an outcome and a predictor, you need a multivariate model to be able to estimate all of that simultaneously. Yes, there are ways to do this via a million separate regressions, but that's less than ideal. We want to be consistent in how we're treating negative mood, because if I put the first path in the model, so if I had stressors predict negative mood, then in the analysis, the variance components of negative mood would be carved up as latent variables by the model into a random intercept and a residual. But if I did this path right here using univariate software, I can't ask the model to carve it up. I'd have to do it with person mean negative mood. And so then to talk about an indirect effect would be weird, because this slope would be using a latent outcome, but the same variable would be treated as an observed box with respect to this slope. So there's an inconsistency if you try to do it in a stepwise fashion that is less than ideal. So we're going to do everything simultaneously. I'm going to show you the models in each step, though. I'm not going to start with the big one. And I would recommend this to you as well. Whenever I do analyses involving a lot of variables, and 3 is a lot in this case, I like to know what the bivariate relationships are before I put everything together. Because I want to know, what is the relationship between stress and physical symptoms to begin with, and then the full model will tell me how different that relationship is after I control for negative mood. So I like to have all the pieces. All right. Any questions about the story or the setup here? Not yet? Zoomers? All right, so we're working with direct effects first. An indirect effect is a term that refers to literally the multiplication of 2 paths. And that is something that you can do in M+ by asking for it to multiply the 2 slopes together. So it's I guess technically it's still a linear combination. It's just multiplication rather than addition. The p-values for those things, though, literature suggests that some sort of bootstrapping confidence interval thing is necessary, because the p-values that come out of this are not quite as good as they should be, but I've never seen it matter in any place past the 3rd decimal. So that's just going to be an example of something Lisa doesn't care about. But reviewer 3 may. So do the bootstrappy confidence interval thingy. That is not always possible in M+. Like for multi-level models, at least I don't think it's possible. They're continually adding things, and so it may be by this point, but at least when I initially built this handout, it wasn't possible. So, all right. So first things first then. So I've got a lot of words here because this is describing what's going to happen, but I'll just show you what's going to happen. Step 1 is x to y. So we're looking at what is the relationship between stress and physical symptoms before controlling for negative mood. Let's find out if these two things are even related. So I have a parallel model in Stata Mixed, R-Elmer, and M+, because I'm treating stress as an observed variable. I can do the same exact thing in any package. This is just a univariate analysis. So the mixed code, or the Elmer code here, I'm controlling for gender and age, as well as their interaction. That was an analysis that I did in chapter 7 of the book to build that part of the model. And with respect to stress, because level 1 stress is binary, I'm leaving it alone. I'm not trying to person mean center that. That means the effect of person mean stress centered at 40 in the level 2 model is going to be a contextual effect because of the way that I set this up. But no worries. I can get the between person effect as the sum. So within plus contextual is between. I'm using maximum likelihood in Stata and in R so that it will match the output that I get out of M+. Otherwise, if I used Dremel, then I would get a little bit differences in the variance components and the standard errors. On the M+ side, zoom in a little bit here so you can see all the tiny code. A reminder that exclamation points, the green text, those are comments. I have a lot of comments in here so that my code hopefully will be understandable for folks who don't know how to do this. So as usual, all the names of the variables that are in your data set in order, each one can only be 8 characters. And then all the variables that are in the model. So I've already helped a few people with this problem. If you forget this, what do you think it's going to do if you don't specify use variables?
Will it not do anything?
Oh, it'll do something.
Oh, it'll just go in the order of like which variables are first in your data set.
Well, so it knows what your names of the variables are because you have names. The question is, what if I forget use variables? It uses all of them. So every variable in your data set is going into the model as a box that's just like floating there, like without being associated with anything else, including things like the ID number. So yeah, it'll run. You'll probably have terrible fit because you have all these things that are likely related sitting in your model telling it that it's unrelated. So use variables is very important. It does not care about the order of variables in terms of you listing it here as it is in the data set, so you can write this part however you want. But you'll note that I had to make a new variable for the interaction term between age and gender. And because that interaction variable is not in my data set, it needs to be at the end of the list here. That's one rule. Make sure you got your missing data code. You can have it be variable specific or general. It wants to know your level 2 ID. By the way, those of you who have asked about clustered sampling corrections, so let's say that you have a 3rd level and you don't really care about it and you just want to like make it go away. If you added another variable in front of here, like school ID or something, and then type equals 2-level random, you would add the word complex. That's all it takes. Then it will adjust the standard errors for the dependency of persons within schools, for instance. However, it will estimate smushed effects for everything because the variance of the school is still in there. So this is not an ideal solution, but this is like, if you can't do anything else, at least do this, if you have another level that you're needing to worry about. So this is ideal when you wouldn't have that many schools. You don't have much inter-class correlation due to schools. You just need to control for what you do have. All right, let me put that back so I don't mess up my handout for the future. Then these ones. Nope, these two. Within and between variables. If you have an observed variable that is level specific, like you only want to respond, let me put it this way. You only want to put relationships in that one level. Like stress is a level 1 variable, I'm putting it on the within. Now, if I don't have person mean stress in the model, so if I didn't have that, and I just do a level 1 effective stress, what would happen to it? Smushed effect. So even though I'm telling it it's a within variable, the variance in it is still there if it's not been person mean centered. So I'm fixing that by controlling for person mean stress at level 2, which will turn it into a purely within effect. So these are my covariates that are observed boxes in this analysis, including age by gender. I'm using ML. If you have concerns about non-normality of these outcomes, you can do MLR instead. I would recommend that as a default, actually, but I wanted to make the models comparable across software packages in this case. Then we get into the within and between models. So a lot of this is going to be default estimated, but I want to write it out so that you know everything that's going on. So in the within model, I'm referring to symptoms. If you list a variable by itself, you're referring to a variance or a residual variance. So this is my level 1 residual variance for my outcome Y. I am defining a slope. Stress is predicting symptoms, and I am creating a placeholder for how that slope could become a random effect. So if you want to have cross-level interactions or the potential for random slopes, you have to set it up this way. I call this the placeholder notation in the article that I wrote describing between versus contextual. So I have named this within person X to Y, keeping track of the X, M, Y structure. That way you don't have to pay attention to the variables per se. So even though I've defined the level 1 slope here, its parameters are in the level 2 model. So within person X to Y in the bracket there, that is the fixed slope. Within person X to Y at 0 means please don't give me a random slope variance for it. This is a fixed slope example. It's an empirical question whether you would need a random slope variance. I don't believe we needed one in this, but it would be a smushed slope variance because I'm using stress as an observed variable without person mean centering anyway, so I don't want to do that. Out here, this is just a label. So if you use words or numbers and they're not repeated anywhere else in your code, like this is just one label. The reason to do it is so that you can make M+ do math for you. I also do it for transparency in my handouts. So symptoms in bracket is the fixed intercept for Y. Symptoms outside of the bracket is the random intercept variance for Y. Then we get all of the level 2 predictors. So gender, age, their interaction, and person mean stress are all predicting symptoms. And I have the latter labeled as con X to Y because this is going to be a contextual effect. That's what the level 2 effect is directly when you don't use person mean centering. So to get the between effect, I'm going to invoke model constraint, which is a way to make it do math or a way to enforce constraints. It does both. Any new term that you're creating out of math, it wants you to create a name for it first, and you put the name in this new command right here. And so BP X to Y is the between person effect that results from the within plus the contextual. Okay, any questions on that? Note that I have 7-Up today. I've already hit my limit of caffeine, so. Nothing? We're good? Okay, all right, cool. So here's what we get back. I have the results from, looks like, Elmer over here, and I have the results from M+. Minus 704 is the log likelihood, minus 704 is the log likelihood. All of the estimates match to at least 3 decimal places. This is the same. The difference is in where things are labeled. So if we get practice over here, what is 0.613? What would I call that? What does that number mean? Right here.
That the leftover level 1 variance, or
Yep.
unexplained variance.
Yep, leftover level 1 residual variance. So the 0.6, there's that, where it is. Then we get to between level. So here are my level 2 slopes. We've got gender difference, so women are reporting fewer symptoms if they're 80, more symptoms as you get older, and the gender gap grows with age, it looks like. So, or I could say that the age effect is reduced and basically eliminated in women. So this is the age effect in men specifically. Then we get this thing, which is my contextual effect, 1.33. So the variable that it applies to is person mean stressors predicting symptoms. Anyone feel brave and want to put it in a sentence? 1.33 is the number.
So would that be, is that the fixed slope?
It is a fixed slope because this is the person mean variable, and there are no interrobangs in this story.
Okay, so between, and is it months? Is
Uh,
that the,
Nope, it's over a 5-day period, and they're reporting
Okay.
physical symptoms per day and whether or not they had a stressor per day, and this is the person mean of stressors.
okay, so for each day that passes, their symptom, or the stress grows by 1.335.
Not quite. So the stress grows makes it sound like stress is the outcome, and stress is the predictor here.
The symptoms,
Yeah, symptoms
They-
grow,
yes.
but
Um,
what are the units though? It's not per day.
It's per point of
Yes.
whatever symptoms is being measured in.
Well, it's per unit of stressors as the predictor. And so this is the person mean of a binary variable. What is the smallest value it can have?
0.
0. What's the biggest value it can have? 1.
1.
Right? All the days, because this is proportion of days. So this coefficient represents the difference between a person who had no stressors ever and who had a stressor every single day. From 0 to 100% is a unit in this analysis. Does that make sense?
So how do we deal with the centering on point 4 then?
So it's centered at point 4, meaning that the intercept for symptoms is the expected average physical symptoms for an 80-year-old man who had stressors on 2 out of the 5 days. But when you have a person mean of a binary variable, a unit is the entire variable, like the whole span. So one thing that I've seen people do is just move the decimal over, like this, and be like, for every 10% more stressors, your symptoms go up by 0.13. Talk about it in terms of every 10% rather than every 100%, as that way you can think about the fluctuation a little bit. That's allowed, yeah.
Okay, because that makes, I don't like that it's just like all or nothing, so I like that you can just. Okay.
Yeah, you can do whatever you want to your coefficient to make it interpretable. Yes. Yeah, yellow hand, I see one this time.
Yeah, I had basically the same comment, Lisa, regarding that effect. For example, if we have 5 occasions, we could divide that coefficient by 5 and then treat the new coefficient as a 1 unit change, which would be have basically 1 day stress or more.
Yeah, that's that you could also do it that way. If in this case divide by 5 and it's for every additional day you have a stressor, your average symptoms goes
yeah.
up by that.
Yeah, and the other thing, Lisa, to me, that coefficient right now would be the incremental effect of having more stress than other people after controlling for the absolute value of stress at level 1, right?
Yep, and that's the other part of the sentence we haven't gotten to yet. Is that this is after controlling for whether or not you had a stressor that day. This is the extra incremental contribution of essentially the number of days you had a stressor. The context of being you. It's not just today, you're you every day. Yep, that's exactly right. So putting it together, for every unit change in person mean stressors, which is going from none to all, average physical symptoms goes up by 1.33 after controlling for whether or not you had a stressor that day. And by the way, there are words at the end of this handout too. As usual, I have an example results section. So at least some of what I'm saying is written down. Okay, now what's this thing? The mean of Wx to y is 0.11. What the hell is that?
I want to say that's a variance estimate within each day.
It's a mean though.
So the average variance within each day of X to Y. My brain is blanking.
Yeah, you would think that it's some kind of relationship like that, but no, this is the level 1 slope. So over in the Elmer model, that number is the slope that goes with level 1 stressors, 0.11. There they are. The reason that level 1 slope is showing up in the level 2 model is because we use the placeholder syntax, where what we have done is create a latent variable whose mean is the fixed slope and whose variance would be the random slope variance if I had it in the model. Otherwise, if I had forgotten this part or left it out, then the level 1 slope would show up directly in the within model. But you couldn't then add onto it a cross-level interaction or a random slope. Yeah, this output can be tricky if you're not used to it. So I'm trying to get us used to looking at it from this perspective. Intercepts for symptoms, that one's a little more obvious, maybe. It actually is an intercept. They got the label right, so there's that. This is my fixed intercept. So at the reference value of all my predictors, a man who's 80, who had stressors on 2 days, on a day he didn't have a stressor, has symptoms of 1.586 on average. This, I think, is a Likert scale of some kind. It's an item average. Variances of within person X to Y, that's where my random slope variance would have been, had I put it in the model. And then residual variances of symptoms. What is that? Yeah, that's random intercept variance left over. Residual means left over. Not to be confused with residual variance at the within level, which is leftover residual variance in the way that we talk about it. So in M+, residual just means leftover. Likewise, the difference between mean and intercept is conditionality. A mean is like from an empty model, essentially, where there's no, the latent variable is not being predicted by anything. So the factor mean is the fixed slope here. Whereas for symptoms, because symptoms is predicted, its factor mean is an intercept instead. I just lost the plot, didn't I? Okay, never mind. Okay, mean is unpredicted, intercept is predicted. Okay, good with that?
Wonderful.
Excellent. Likewise, variance, unpredicted. Residual variance, leftover predicted. And let's see, did we get everything? Last but not least, my between stress slope. So without controlling for whether or not you had a stressor on that day. And so that is computed from the level 1 fixed slope within plus the contextual slope at level 2, gets me to the full between at level 2. So far, if we look at the p-values of these things, does stress translate into additional physical symptoms? Or is that too simplistic of a question? By the way, p-values are in the last column. Make it bigger? I can scooch it or scotch it. So my question was, does stressors translate into increases in physical symptoms? Or is that question specific enough?
Not the more than usual day, so.
Yeah,
not within person level.
on the within person level, no. There is no relationship between whether or not you had a stressor that day and your symptoms on that day. How about on the level 2? Yeah, so whether we think of it as contextual or between, same pattern. People who report more stressors also report more symptoms than other people. But on a given day, you're not more likely to report more symptoms if you happen to have a stressor that day. So this is a cross-sectional relationship, not really a longitudinal one. Okay. How are we doing so far? 2 thumbs up. Woot! So up to this point, there's no reason to bring M plus into the picture. Now is the point where we bring M plus into the picture. So step 2 is looking at how mood predicts symptoms. And the question is, how are we going to control, or how are we going to treat mood, observed or latent? So stress is not in the model right now. We're just looking at whether negative mood and physical symptoms are related bivariately. So over in the left-hand side, I have step 2-ish in the title, because these models are not equivalent. If I'm using a univariate software package where I can only predict one column longitudinally, then I have to take my time-varying predictor and carve it up into the level 1 part and the level 2 part. To make it comparable to the previous model, I'm still using constant centering here, where I just have mood centered at 2 at level 1, and then I have person mean mood centered at 2 at level 2. And I can get the between effect by adding within and contextual together as before. So if I do that, here's the output that I get. It looks like I have a significant contextual effect of person mean mood, and it looks like I have a non-significant within effect of mood. So based on these results, I would say if I feel grumpier than usual, that does not translate into more symptoms than usual at that occasion. But people who are grumpier than other people report more symptoms than other people, with scientific notation being used in the p-value, it's so small. And so then we have a significant contextual effect as well as a significant between effect. Now if we go to the M plus side, this is a different model. It's the same idea, but it's not being implemented the same way. So first off, mood, as my level 1 predictor, is not here. Within is empty, because I'm going to let the model divvy up mood into its between and within parts. I'm not doing it with observed variables. So I'm just using mood centered at 2 so that my physical symptoms intercept will be meaningful. So now I have this new term relative to what we saw before. That's going to be my level 1 variance in mood, in the same way that I have level 1 variance in symptoms. So that's a new term, because now the model parameters involve those of X, not just Y. Mood is an outcome. It's just not being predicted by anything. I still have my within person slope. Now it's from M to Y rather than X to Y, defined with a placeholder. That shows up in the level 2 model. As before, I'm estimating a fixed slope and shutting off the random slope variance. I don't want that in my story yet. I have these new terms in the between model as well. I have the fixed intercept for mood, which is its mean, as well as its random intercept variance. So at this stage, what we have visually is going to be this type of model, where X is carved up into latents instead of observeds. Because mood at the within level, no, actually, let me back up. Because I use this placeholder notation to define the slope of mood predicting symptoms, that automatically, when you're using maximum likelihood, makes it so that the level 2 effect of mood on symptoms is the contextual effect. If I fit this exact same model using Bayes, it's between instead. I know. Can I tell you the story about that? About the paper? Have I told you the story about this? I feel like maybe I have. But it's probably a good time for a story because it's getting a little bit much. So the people that made M+ published this article in the Structural Equation Modeling Journal. They have a section of it called Teacher's Corner that's meant for tutorials. And when M+8 came out with all this new Bayesian stuff to it, they put this article in there that says you need to use Bayes, and here's why. And they did a simulation where they estimated the same model in ML, and then they estimated it in Bayes, and their conclusion was that the ML level 2 slopes were biased, whereas the Bayesian version retained the correct version. But they did not recognize that the reason they were biased is because they were contextual slopes and not between slopes. And once you correct for that difference, they are spot on the same. So I felt like it was disingenuous, the way that they approached it, to call it bias as opposed to an alternative parameterization. So I wrote a paper about it. And it got published for once, so hooray. Not always. Okay, so then if we look at the results over here, we have this thing on the between level, this thing for the within, that would be the random slope variance, and then the between slope. So this would be the analog of having person mean mood predict symptoms. But it's not the person mean as an observed variable, it's the random intercept for mood that's doing the work here. So this is the contextual slope, and it's 2.3. In the observed variable version of the model, it was only 1.8. So this is another common result, that your level 2 slopes will be stronger in the latent version of the model because it's supposed to be correcting for measurement error. In multi-level models, I had this in here, the way that the intercept variance is estimated, you might remember this formula from last semester. They take the observed variance in the person means, and they subtract off a correction factor for how much of that would be expected just on like random chance. And the correction factor is the residual variance divided by the level 1 sample size, so the number of occasions here. And that gives us the true estimate. So when we do person mean centering and we use the observed person means, we're using this number, whereas M+ is using this number. So it's trying to correct off the unreliability, and the relationship that's left is supposed to be the true one. So by the same logic that people say you should use structural equation modeling over path analysis because your relationships are disattenuated for measurement error, it's the exact same situation for this. So this result, that you end up with a stronger level 2 effect when you let the model divvy up the variances for the predictor, is known as Lüdke's bias. There's a 2008 paper on your reading list, was the first person to really call out this as a thing. So that would be a potential advantage of doing it this way. Besides just the fact that you're treating X and Y in a parallel structure, your level 2 effects may be stronger. The level 1 effect, 0.167. In the observed variable model, it is 0.159. So also a little bit different. Usually level 1 is not affected as much as level 2. One more piece here to this. So here is the alternative way of putting in a level 1 effect without a placeholder. So if I just write the regression of mood predicting symptoms and I don't have the within person M to Y thing in the front of it, then now all this can possibly be is a fixed slope, first off. So you can't do it this way if you want to have a random slope or a cross-level interaction. But if I do it this way, note that the references to within person M to Y that were in the level 2 model are gone because they're in the level 1 model instead. The other thing that changes when you're using ML estimation is that now the level 2 effect is between instead of contextual. So the output then looks a little bit different, and I put them so that you can compare them across. So now here's my level 1 slope. It shows up in the level 1 model. There's no within person M to Y mentioned because that is not a defined variable in the analysis. The mood slope that I get is the between version, 2.5, that I had as a linear combination when I had the placeholder notation. And I estimated a linear combination to get the contextual slope in this model that shows up by default as the mood slope over here. So here is a pro tip. One strategy that you can use to figure out if something is between or contextual. Switch, to your point, switch this to with. Here's why. If you change the level 1 effect into a covariance instead, and the level 2 slope changes, that means it's contextual, because it's not controlling for something. If the level 2 slope stays the same, it's between. So that is one thing you can do to make sure you know what you're looking at with these things. If you switch to Bayesian estimation, then everything becomes within between. Nothing's contextual. And some of the other advances that they have for longitudinal, intensive longitudinal data require Bayes. You can't even do them in ML. So we'll see some examples of that next week. All right. Once again, I was optimistic in how much we get through, but that's always the case. That's the one constant, is that I'm always terrible at predicting how long things take. But we're halfway through, so there's that. All right, 139. I think that's a good place to pause for today. Step 3 we'll do on Thursday, which is to fit the full mediation model, plus a couple extra things involving moderation. So to foreshadow that very briefly, let me put my picture back up. Here's my model structure, right? What if I wanted to know whether my between person slope varied by gender? If the relationship between being grumpy and feeling sick was different between men and women. Could I do that? Seems like a question I could answer. So if I were doing person mean centering, I would take this observed variable and multiply it by gender and put a new interaction box in my model, right? Or age or anything else. How do I do that when it's a circle? How do you multiply a box in a circle? You don't. So one of the things I want to show you in this is how to fit latent interactions, latent variable interactions, an interaction circle, essentially, which is required when you switch to this type of setup where the relationship is coming from a latent variable to another latent variable. The bad news is that those types of models require numeric integration of some kind, which means it's even more complicated to try and estimate. So moderation is much easier to do with observed variables than latents, but it is possible to do them with latents. So we'll see an example of that next time. All right. Any questions before we call it a day? Yes.
So I was trying to look at the differences between the models for the Loonkes bias.
Mm-hmm.
So I noticed that we have 1.1 or 1.8
This one, okay.
And
Mhm.
then, if we go down to the corresponding contextual effects, down here, we got 2.340.
Yes, right here.
So the parameter estimate is inflated, right? Or the estimate is inflated.
Some would say that this is the right version and that the observed variable one is downwardly biased.
Okay, but higher.
Higher, I'll give you higher, yes.
And, but the standard error is also higher.
Mm-hmm.
The t-value is lower. So I
Mhm.
guess I'm just trying to understand is the bias just on the estimate? And standard error is t-value, that's a different? I'm just
So-
trying to be concerned about like significance testing.
Yeah, so this is also part of what they found in their simulation, was that the standard errors were higher because they're reflecting the uncertainty that we had to figure out what the random intercept was before we could show how it predicts this other thing. And there's just more uncertainty in doing that. So the standard errors for these fixed effects are bigger because they're realistic. Because what we did before, making a person mean mood box like pretends it's a perfectly measured observed variable, and we know that it's probably not. So there's a sense in which the latent results are probably like theoretically more believable, but they are necessarily noisier.
So, and because the t-value is lower, it's more likely to, on the margins, we're probably gonna get more chance for a significant effect in the univariate land.
It's usually that there's a stronger effect at level 2, even despite the standard error. Yep, that's the pattern that has been shown, at least in the literature on this. So, all right, thanks for being here, folks. Happy Garbage Day. Let me know if you need anything, and I'll see you on Thursday. Bye, Zoomers.